Morning to everyone, and this is Shiv Kumar sir. Welcome to the Gate MentorAcademy.com. So today we are going to start a very important property. It's a viscosity. So it's a very important property is there in fluid mechanics. Viscosity, everywhere you need a viscosity terms. So we'll start that here. Viscosity. It is defined as it is the internal resistance offered by one layer of fluid over another layer is called a viscosity. Or viscosity, we can say that in another term, like it is a resistance to the flow of a liquid. Resistance to the flow of a liquid. Why the liquid stops? Because of viscosity. Viscosity will create a resistance. Like if I'm assuming that this is the flat plate is there, and if I'm going to pour a water on this surface, the water will get stops after traveling some distance. Why? Because of the one resistance which is acting just opposite to the motion of the fluid, and that resistance is called here viscosity. So here we'll define that there is one law is there. That law is called a Newton's law of viscosity. Newton's law of viscosity. So that Newton's law of viscosity says about the shear stress. Whenever the fluid is flowing over the flat plate that is in parallel way, one shear force will generate. This force is called here a shear force, and the shear force will cause here shear stress. Shear force means what? The force which is acting parallel to the surface. Parallel to the surface is called here shear forces. So that Newton's law of viscosity says about that the shear stress is directly proportional to the velocity gradient, or angular deformation. That is a rate of angular deformation or rate of shear strength or rate of shear strength. So the shear stress is denoted by a tau, and that tau is directly proportional to d theta by dt, where this d theta by dt is called a rate of angular deformation, or it's a rate of shear strength. And this tau is named as a shear stress, is defined as shear force upon contact area, and that is given as F by A. So here we'll assume that one flat plate, let's say that this is the one surface is there, and we are going to apply a one shear forces. If you apply the shear forces, this end will shifted through some angle. So similarly, this end will also shifted through a same angle. So let this angle is a d theta. So this angle will be also a d theta, and this flat plate that deformation, I'm assuming that this theta due to the velocity v. If you apply some force, there must be a velocity. So I'm assuming that the velocity is v. So let's say that the initial velocity of the fluid is u. So this will be also u. So I can say that here, this distance, this is here, it's a deformation. Which deformation? It's a linear deformation. So what about the linear deformation? And let's say that this linear deformation is represented by here v. So here we can say that the velocity is given as, let's say that the velocity is indicated by u is equal to d by t. So the d is here u into t, but distance is a scalar quantity. So if you take the derivative, so it will be du into dt. So this d we can replace it by here du into dt. So if you take that here tan theta, tan d theta, so tan d theta will be perpendicular, will be this one, and the base will be this one. Let's say that the height of the parallel surface is dy or thickness is dy. This is called here thickness or height of this parallel surfaces. So it is given as du into dt divided by dy. Tan theta is equal to. So since d theta is very small, hence tan d theta is assumed as d theta. So that d theta is equal to du into dt divided by dy. So d theta by dt, it must be equal to du by dy. It's a very important result. I got it from here. So this d theta by dt is called here rate of angular deformation or rate of shear strength. And this du by dy is called here a velocity gradient. Velocity gradient. So I can say that by Newton's law of viscosity, that tau, we know that it's a directly proportional to d theta by dt, or else we can write on using this relation, tau is direct proportional to du by dy. So here the shear stress can vary with respect to velocity gradient or with respect to rate of angular deformation or rate of shear strength. So this proportionality constant is removed by mu into du by dy. So this mu is a very important here. Mu is called here, it's a dynamic viscosity. Dynamic viscosity. And the unit is Newton second per meter square. And if you write on the dimensional formula, then the dimensional formula is ml minus 1 t minus 1. This is the dimensional formula is there. You can derive it here by using dimensional formula for force second and the meter square. So this is important. So I'll go to the next page here. That tau is equal to mu into du by dy. If you assume that change in velocity is v and the change in thickness is y, so and the shear stress is named as a F by A is equal to mu into v into y. So the shear force is given as mu A V into y. It's a very important result to find out the shear force. To find out the shear force. Next, we'll see that here variation of viscosity with respect to temperature. So before that, there's a unit is there, unit of viscosity. Unit of viscosity is Newton second per meter square, and the viscosity is also measured in poise. So the 1 Newton second per meter square is equal to, remember that it's a 10 poise. or 1 quiz is equal to, remember that it's a 10 raised to minus 1 Newton second per meter square. So if the dynamic viscosity is given like 0.5 quiz, it means you can write down in a standard unit, it's a 0.5 into 10 raised to minus 1 Newton second per meter square. So the unit is very important here. Unit is very important. So here we can say that one more concept you remember that here. This is the tau, that is a shear stress. So if you assume that if the rate of angular deformation like d theta by dt, and its the rate of angular deformation is, if it is large, then the flow is easy. It means resistance is less. And if resistance is less, the mu should be also less. So if d theta by dt is large, it means the flow is easy. But if the d theta by dt is small, like that, say, if d theta by dt is small, resistance is large, means the flow is not easy. And it means the resistance is more and the mu will be high, because mu is actually, it's a resistance to the flow of a liquid here. So you remember that d theta by dt, and its rate of angular deformation अगर large होता है, flow will be easy, or resistance is less, then mu is less. Next, we'll move it to the next properties. It's a kinematic viscosity. That is called your dynamic viscosity. This is your kinematic viscosity. Kinematic viscosity is represented by nu, and it is given as, it's a ratio of dynamic viscosity divided by density of fluid. So it's given as mu by rho, and the unit of kinematic viscosity is, it's a meter square per second. Meter square per second. So the kinematic viscosity is also measured in Stokes. And the Stokes is named as a centimeter square per second, is given as Stokes. So the 1 Stokes is given as 10 raised to minus 4 meter square per second, because 1 centimeter is equal to 10 raised to minus 2. So 1 centimeter square is equal to 10 raised to minus 4 meter square per second. So this is their Stokes. Or sometimes it is given 1 centi twice. 1 centi means 10 raised to minus 2, and twice means 10 raised to minus 1. It is given as totally 10 raised to minus 3 meter square per second. Not meter square per second, it's a Newton second per meter square. Twice is a unit of dynamic viscosity. So this is the also one more way to convert. Next, we'll see that here variation of viscosity with respect to temperature. Variation of viscosity with respect to temperature. First one is, I'll take it here, in case of liquid. So I'm assuming that here any type of liquid is here, and what will be the effect of temperature on viscosity. So you remember that in a liquid, the intermolecular distance is small. Hence, cohesive force is large. It means with a rise in temperature, this intermolecular distance, it will increases and the cohesive force decreases. And if the cohesive force decreases, resistance to the flow also decreases. So here I can say that the viscosity also decreases. So with rise in temperature, the cohesive force, because the bonds will break in between. So I can say that here the intermolecular distance increases, cohesive force decreases, resistance to the flow also decreases. Resistance also decreases. If the resistance decreases, it means the viscosity also decreases. Means I can say that if the temperature will increase, the viscosity will decrease. The viscosity will decrease. So there is a relation between the viscosity and temperature is given as mu is equal to mu naught plus 1 plus alpha t plus beta t square, where alpha and beta are the constants, So this is the variation of a liquid gas is given. Similarly, in case of gaseous case, because the T is always inversely proportional to mu in case of liquid. But in case of gaseous, the cohesive force is negligible because the intermolecular distance is very, very large. So if you increase the temperature, molecular disturbance increases because the molecules will gain the energy and their randomness increases. That is called molecular disturbance increases. Hence, resistance to the flow also increases. Resistance to the flow also increases. If resistance increases, it means the viscosity must increase. So in case of gaseous case, you remember that if the time in temperature increases, the viscosity also increases. So the viscosity is directly proportional to temperature in case of gaseous case, where alpha and beta are the constants. So if you want to make the diagram for liquid and gaseous case, so this side is mu and this side is a temperature is there. So for liquid case, it will like that because as the time increases, the viscosity decreases. And in case of gaseous case, the graph for this one. So this is for gas and this is case for a liquid. So this is the variation of a viscosity with respect to temperature. Next, we will see that here, based on the Newton's law of viscosity, we'll differentiate the types of fluid. So we'll check that here, type of fluid. So there is a, first of all, there is a two type of fluids are there. The first fluid is a Newtonian fluid. Newtonian fluid. Newtonian fluid means which follows the Newton's law of viscosity. Follows the Newton's law of viscosity. यहाँ से एक क्वेश्चन पूछे जाते हैं एग्जाम में. Keep in mind here, remember that we will discuss here all types of fluids. What are the types of fluids are there? Time dependent, time independent fluid, non-Newtonian fluid, everything we'll discuss it here. Which follows the Newton's law of viscosity, that is called a Newtonian fluid. So the tau is directly proportional to du by dy. And if you want to make a diagram, it's a directly proportional means you will get a here straight line between the shear stress and the velocity gradient. And there is a next type of fluids are there here. It's a non-Newtonian fluid. non-Newtonian fluid, which does not follow the Newton's law, which does not follows the Newton's law, is called non-Newtonian fluid. And tau is not proportional to du by dy. Yani there is some different equation. There is a different equation. A different equation that it is given as tau is equal to a into du by dy to power n plus b. So this is the non-Newtonian fluid equation. And that non-Newtonian fluid is further divided into two types. The first one is it's a time independent, that does not depends upon time. It's a time independent. And the next one is here time dependent. Time independent, there is a three types of fluids are there. The first one is a pseudoplastic fluid. Remember that condition for the pseudoplastic fluid, the N must be less than 1 and the B must be 0. That is called pseudoplastic. I will write down here. It's a N less than 1 and the B must be 0 here. This one, N must be 1 and the B must be 0. And it is also called a thin fluid. Remember that it's a thin fluid. And the example for pseudoplastic fluid is blood, milk, tent. Blood, milk, tent, etc. That is a pseudoplastic fluid. Next, we have a dilatant fluid. Dilatant fluid. For dilatant fluid, it is also called here thick fluid. That N must be greater than 1 and the B must be equal to 0. So the example for a dilatant fluid is sugar syrup, butter, sugar syrup, butter, quicksand. So ये सभी फ्लूइड को बोलते हैं यहाँ पे, it's a dilatant fluid. And the next one we have a Bingham plastic fluid. Bingham. Okay, this is not there. H is not there. Bingham plastic fluid. Bingham plastic fluid is that N must be equal to 1, B cannot be equal to 0. And the example for Bingham plastic fluid is here toothpaste. Toothpaste is here Bingham plastic fluid. Remember that. Only remember that condition is important. Next, we have a time dependent, and the time dependent is divided into two types. Time dependent is divided into two types. The first type of fluid is thixotropic, and next is a rheopactic fluid. Thixotropic means B cannot be equal to 0, N must be less than 1, and if the time increases, the viscosity decreases. So what could be the type of fluid for the thixotropic? It's a ice cream. Ice cream, first of all, it's a solid is there. उसके बाद थोड़ा टाइम होने के बाद वो मेल्ट करने लगता है, तो उसका विस्कोसिटी डिक्रीज होने लगता है. या yogurt is here also a thixotropic, or margarine is also a thixotropic fluid. Next, rheopactic. B cannot be equal to 0. N must be greater than 1. And as the time increases, the viscosity also increases. The viscosity also increases. So we can say that it's a gypsum paste. Example, gypsum. यानी liquid से solid में जा रहा है, that is called gypsum paste. या bentonite solution. Or else we can say that blood also it's a reactive. Blood get clotted. And the diagram for that, this type of fluids are there. Diagram I can draw that. Tau is equal to, okay, this side it is mu into du by dy. This diagram is for a Newtonian fluid. This is for your dilatant. N must be greater than 1. This is for pseudoplastic fluid. N must be less than 1. A straight line, one more, that is a Bingham plastic fluid. This is for, it's a thixotropic. And this is for a rheopactic. And this gap is given as here B. So the important is here condition, like what could be the condition for B and N, that is important here. Many times they have asked the question based on that condition. So next we will see that the question based on that. And we have lots of questions based on that. We'll start that here. Just okay, 1 second. Good morning to everyone. Good morning to everyone. Okay, we'll start the question based on that Newton law of viscosity. So the question number 4, the kinematic viscosity of a gas at 20 degrees Celsius is 21.6 into 10 raised to minus 5. And its kinematic viscosity at 70 degrees Celsius is. So see, it is given for gas. For gas case, we know that if you increase the temperature, the viscosity must be increased. So at 20, it's a 1.6. So at 70 means it should be more than 1.6 into 10 raised to minus 5. It should be more than means I can see that the only D option is satisfying, and it's a 2.2 into 10 raised to minus 5. It's a more than 1.6 into 10 raised to minus 5. So I can say that the option number D is right answer. Next, we have a question number 5. The shear stress developed in a lubricating vial of viscosity 0.981 poise filled between a parallel plate 1 centimeter apart, moving with a velocity 2 meters per second. We need to find out the shear stress. So I'll go by the Newton's law of viscosity. As we know that the shear stress is directly proportional to velocity gradient, and it is given as mu into du by dy. So shear stress is tau, and it's given mu is given here 0.981 poise. Write down into a standard unit, and it is given a 0.981 into 10 raised to minus 1 Newton second per meter square. Okay, Newton second per meter square. So use it here 0.981 into 10 raised to minus 1, and the velocity is given 2 meters per second. And the parallel plates, these two are parallel plates, and they are apart 1 centimeter. And in between there's a lubricants are there. So I need here this distance, that is gap between the parallel plate, and that is given 1 centimeter. So I'll write on 1 into 10 raised to minus 2 meter. So that tau is equal to, we can write on here, this one will go up and it will be 0.981 into 20, and if you simplify them, you'll get it here 19.62 Newton per meter square. So the option number first is right answer. So the simple best formula is there, and these all are the previous year question paper is there. Next question, we'll see that here. The velocity distribution over a flat plate U is equal to given 3 by 4 y minus y square, and the shear stress at a location of 0.3 meter above the plate is k times the shear stress at 0.2 meter above the plate. Then what is the value of k? You need to find out. So the one condition is given, the given data here it is given that U is equal to 3 by 4 into y minus y square. And the next important data is given, shear stress at 0.3 must be equal to k times of 0.2. So that shear stress, we know that it's a mu into du by dy by the Newton's law of viscosity at 0.3 must be equal to k into mu into du by dy at 0.2. So I need to find out the value of k. So I will try to find out here a du by dy, that is a velocity gradient, and it is given as 3 by 4 minus 2y. So find out the du by dy at 0.3. Y is equal to 0.3. It means so 3 by 4 is given 0.75 minus 2 into 0.3. So 0.75 minus 0.6, you will get it here 0.1. Similarly, you find out the du by dy at y is equal to 0.2. It's a 0.75 minus 2 into 0.2, and it is given as 0.35. So that value is substitute in equation number 1. So this mu get cancelled. It's 0.15 into 15 by 35, and it's a 5 3 the 5 7. The answer will be a 3 by 7. The k value is a 3 by 7, and it's a option number A is a right answer. Similarly, we have a next question. A fluid obeying the equation tau is equal to tau naught plus k into du by dy to power 1 by 2. If held between the two parallel plates d apart, there is a two parallel plates are there, and the distance between them it is given that d, and the plates are moving with a velocity b here. If the stress applied to the top plate is 3 t naught, then the velocity with which top plate moves. So the stress is given that tau is equal to given here 3 t naught, and the one equation is given that tau is equal to tau naught plus k into du by dy to power 1 by 2. So I need to find out the velocity of the plate. At what velocity the plates are moving. This is the one plate is there. This plate is moving over the fixed plate. So that value is substitute here. It's a 3 t naught is equal to tau naught plus k into du by dy to power 1 by 2. It will become here 2 t naught is equal to divided by k must be equal to du means the velocity v and dy means the gap between the plates. So the v is equal to, we can say that it's a 4 into tau naught square divided by k square into d square, and this is the velocity of the plate. बहुत simple है. You need to use that equation and you can find out the directly. And remember that the one plate must be fixed and other plate must move. It should be moving. Another plate must be moving. And this type of flow is called a Cauchy flow. This type of flow is called a Cauchy flow. Remember that, because they have asked the question based on the Cauchy flow also. That one should be fixed and another plate should be moving, and those two plates must be parallel. Next question we have based on the Newton's law of viscosity only. A piston ring of a diameter here 60 mm moves inside a cylinder of 60.1 mm diameter. So there is a piston ring, and the piston ring is your cylindrical shape is here, and that cylindrical shape or diameter it is given here 60 mm. And the another is moving inside another cylinder of 60.1 1 mm diameter. So those two cylinders are concentric here. Those two cylinders are concentric here. And this inside cylinders are moving. And the diameter for this one, it is given here 60.1 mm. Determine the percentage decrease in force necessary to move this piston when the lubricant is heated from 0 degrees Celsius to 120 degrees Celsius. If this is the inside cylinder is there, so this is moving inside the, and this is here lubricant. This is called a lubricant. That lubricant is filled at this position here. So I need to find out this thickness dy. So this dy or this thickness is given as 60.1 minus 60 divided by 2. If you take the difference only 60.1 minus 60, you'll get it here 0.1 mm. And this 0.1 mm means that includes this distance also or this distance also. But I need only thickness of any one. So you divide by 2. It's a 0.1 divided by 2 means you'll get it here 0.05 mm. And 0.05 mm means you will get it here 0.05 into 10 raised to minus 3 meter, and that is the thickness. So here I need to find out here the percentage decrease in the force. So see, we know that here tau is equal to mu into du by dy, and tau is given as force by area, mu into this u is given as v, and this dy I am writing as a y. So F is equal to mu into V into A divided by. So see, remember that here everything is constant except dynamic viscosity. Except dynamic viscosity. Why? Because here the temperature is increasing. Temperature is increasing. And we know that in case of liquid case, as the temperature increases, the viscosity must decreases. So I can say that the force is directly proportional to dynamic viscosity. Force is directly proportional to dynamic viscosity here. So here you need to find out decrease in the force. So there's a one data is there. It's a missing data is given. It's a given mu at 0 degrees Celsius is given 0.0182. 0.0182 Newton second per meter square. And one more data is given here. Mu at 120 degrees Celsius is 0.002 Newton second per meter square. So if you want to find out the percentage decrease in force, we can say that F2 minus F1 divided by F1 into 100. Or else you can write on in terms of dynamic viscosity, mu2 minus mu1 divided by mu1 into 100. And if you substitute the value here, that is a 0.002 minus 0.0182 divided by 0.0182 into 100. And if you find out here, you will get it here approximately 88.68%. And this minus 88.68% is merely to the option number C here. And this minus indicates that decrease in the force. Decrease in the force. So I use the concept of temperature variation with respect to viscosity, and next I use the concept of viscosity. Next we'll see that next question here. Find the viscosity of wire as shown in figure. This is the most repeated gate questions are there. This is the most repeated gate question. So there is one inclined plane is there, and that inclined plane is at an angle theta, and this plate is moving with 0.5 meter per second, and the weight of the plate is 130 Newton, and the inclination slope is given 5:12. It means the tan theta is given 5/12. It means this is the perpendicular and this is the base. So if you make a here right angle triangle, this is a 5/12. It must be 13 here. So I can say that the tan theta value will be 5/13. Sin theta value will be 5/13. To resolve the component along xy direction, along y and along x direction. So this is the weight, that is 130 Newton. And if this angle is theta, this angle will be also theta. So along this direction, we can say that 130 cos theta. And along this direction, we can say that 130 sin theta. So if you apply the here, Newton's law of viscosity, that tau is equal to mu into du by dy. The tau is given as force upon area. The force is F divided by area is A is equal to mu into du by d. The force, I will take it here 130 sin theta because the plate is moving in this direction and the force is 130 sin theta. Area is 1 meter square. Mu I need to find out. Velocity is 0.5 and the thickness between the plates, this thickness. So this is given here 0.5 centimeter of wire. 0.5 means 0.5 into 10 raised to minus 2. So the 0.5 get cancelled. The mu value is 130 and sin theta is 5 by 13 into 10 raised to minus 2. So this 10 times it will get cancelled. If you simplify, then you will get it here 0.5 Newton second per meter square. So the option number C is right answer. So remember that in an inclined plane, if the plate is moving in this direction, I need this component. If the plate is moving upward also, I need this component, that is a horizontal component. Next, we'll check it here. Next question. In an experiment, the following shear stress and the rate of shear strain value are obtained from a fluid. Then the fluid under the consideration is this tau by dt is given in one column and the tau is given in another row. I need to find out that this type of fluids are there. So to find out the type of fluid, I need to find out the value of N and B. Because we have a one equation that is a non-Newtonian fluid, it is given as A into du by dy to power n plus b. This is the non-Newtonian fluid equation I have given. So use it here, and du by dy I can write down here as a d theta by dt also, because the angular deformation is directional to velocity gradient that we have already defined that. So use it. Tau is 0. First condition, the d theta by dt is also 0. So if you use it this equation, I can say that the b value will be 0. So the reduced equation is tau is equal to A into du by dy to power n. So I need to find out the value of n. I got it here, b is 0. Now to find out the value of n, use the next to data. Tau is 1.4. The d theta by dt is 2 raised to n. And next tau is a 2.6 and d theta by dt is 3 to power n. Divide these two equations. This is the equation number 2 and this is the equation number 3. I need to find out the value of n. Because b I got it here, I need to find out n. So this is the, if you divide it here, 14 by 26 must be equal to a get cancelled. So it's a 2 by 3 to power n. So 2 7s are 2 into 13. So I can write down 13 by 7 is equal to 3 by 2 to power n. And if you take the log both the sides, it will be log 13 by 7 must be equal to n into log 3 by 2. So the value of n is given as 13 by 7 divided by log 3 by 2. And if you simplify them, you will get the approximate value as a 1.53. And that is a greater than 1.53, it's the greater than 1. So if the value of b is a 0, b is 0 indicates that it's a time independent. So time independent means there is two type of fluids are there, that is a pseudoplastic and dilatant. For pseudoplastic fluid, the value of n must be less than 1, and that is indicates that shear thinning fluid, that is a thin fluid. And next is a dilatant fluid, and dilatant fluid means the value of n must be greater than 1, and this indicates that here thick fluid. So I can say that the option number D is right because the value of N I am getting here. Because Bingham plastic fluid means B cannot be equal to 0, and pseudoplastic means B is equal to 0, N less than 1, and dilatant means B is equal to 0 and N must be greater than 1. So I am getting the value of N is greater than 1. It's a dilatant fluid. Next question, it's important here. It is given that the shear stress in a fluid may be expressed as mu into du by dy to power n. Then the value of N for which Newtonian and non-Newtonian fluid. For Newtonian, it will be N must be equal to 1. And for non-Newtonian fluid, N should be greater than 1. Yeah, it's possible. N should be less than 1. It's possible. N should be greater than 1. It's possible. And it is also all three possible. But N cannot be equal to 1. This is the right answer. Because N cannot be equal to 1 means I can say that from here, N could be greater than 1. N could be less than 1. These two are the possibility are there. And I can say that the option number A is the right answer. Because from there you can conclude that N is greater than 1, N is less than 1. If you say that N is greater than 1, that is for some specific fluid, like it's a dilatant fluid or pseudoplastic fluid. Next, we'll check it here. That is the last question. Second last question. A piston of 800 mm diameter and 200 mm long works inside a cylinder of 804 mm diameter. If the annual space is filled with lubricant, and this space is filled with lubricant, while of viscosity 5 centipoise, then find the speed of a piston in a vertical downward direction. Take the weight of the piston is 9.42. So I need to find out this thickness, because if you apply the Newton's law of viscosity, tau is equal to mu into du by dy. So that I need here dy. Dy means it's a thickness, and to find out the dy, it's a 804 minus 800 divided by 2. It's a 2 mm. The thickness is 2 raised to minus 2. This side is also 2 into 10 raised to minus 2. 2 plus 2, total 4 mm. There is a 4 mm difference in there. I need to find out what? I need to find out here speed. Find out the speed of the piston, which is moving inside the bigger cylinder. The speed means I need to find out here this mu value. So tau is equal to, we know that it's a force upon area. Mu write down as it is. Speed I am assuming v, and the thickness is y. So the mu value is given here 5 centipoise. So I told you how to convert. Centi is a 10 raised to minus 2, poise is 10 raised to minus 1 Newton second per meter square. It's a 5 into 10 raised to minus 3 Newton second per meter square. And the area is given here pi dl. So pi diameter is 0.8 because 800 mm diameter, because the inner cylinder is moving. So I will take it here that diameter. So 800 into the length is given here 0.2. So that is the here area. Why I am taking here surface area? Why not cross-section area? Because the lubrication is done in the surface, not in the cross-section. So that's why I have taken the surface area. Now apply the formula here. 9.42, that is a load, divided by area is a pi, 0.8 into 0.2. Mu value is a 5 into 10 raised to minus 3. Velocity is v, and thickness is 2 into 10 raised to minus 3. This get cancelled, and if you find out the velocity, you will get it here 7.49 meter per second. If you use it here, you will get it here 7.49. And the answer is option number A is the right answer. Next, we have a question based on the Newton's law of viscosity, and it is given that through a very narrow gap of height h, there is a 2 plates are there, and there is a narrow gap is given. A thin plate pulled at a velocity v. So there is a plate is there, बहुत ही thin plate है, and this plate is pulled with a velocity v of an side of a plate, and there is a viscosity is mu. So there is a one side lubricant is there, and the viscosity is mu1, and on the other side there is another lubricant is there, and the viscosity of other side is mu2. Find the value of y when the shear forces on the two sides of the plate is 0. So if this plate is moving with v velocity, there must be some force. So there is a one shear force which will act, that is just opposite to the motion. And that one I am assuming that F2 and F1. So that F is equal to, I can say that here F1 plus F2. So it is saying that the shear force on the two sides of the plate is 0. It means this one is 0. It means the F1 must be equal to F. The shear force must be equal. So F1 is equal to, we know that mu A V divided by Y is equal to mu A V divided by Y. So let's say that this distance is Y. I need to find it. So then this distance will be here H minus Y. H minus Y. So substitute in that formula. It's a mu1. Area is A. V is the velocity divided by Y is equal to mu A V T divided by H minus Y, because the thickness for the other plate is, it's the H minus Y. So AB get cancelled. So I need to find out the value, Y value. So multiply it here, mu1 H minus mu1 Y must be equal to mu2 into Y. If you simplify it here, the Y value will get it here mu1 H divided by mu1 plus mu2. So this is the thickness of the first plate towards the down. So this is the bottom part and this is the top part. When we add this Y value, the shear forces on the two sides of the plate must be equal. Next, it is given that pull required to drag the plate is minimum. Kitna force चाहिए, so that what could be the minimum force to drag the plate? Minimum force. So we know that the F is equal to F1 plus F2. The total F, pulling force, must be equal to resistance force. So that F is given as mu1 A into V divided by Y plus mu2 into A divided by H minus Y. Now for the minimum, differentiate force with respect to Y and equate to 0. So if you differentiate this one and if you equate to 0, you'll get it here mu1 into A into V divided by Y square into minus 1. And this one you will get it here mu2 into A into V divided by H minus Y L square. If you differentiate, you will get it here this one. Because 1 by Y is there, if you send it up, it will go minus 1 into Y to power minus 1 minus 1. And if you send it down, it will become minus 1 by Y square. So if you simplify here, so this AB get cancelled. It will get it here mu1 divided by Y square must be equal to mu2 divided by H minus Y L square. So further I can say that here H minus Y by Y must be equal to mu2 by mu, then a square root. Then H by Y minus 1 is equal to mu2 by mu. So the H by Y is equal to mu2 plus mu1 divided by root under mu. So that value of Y is given as H into root under mu1 divided by mu1 plus root under mu. So this is the Y value. So remember that if you pulled any plate or any objects in a motion of the plate in a direction, there must be a resistance which is acting opposite to the motion of the object, and that resistance is called here shear forces. So thank you very much, and I'll give this much only. In the next class we'll discuss the concept behind the surface tension and the capillarity. So thank you.